So, welcome back to our YouTube channel, Ruby Structures, where we teach how to design structural elements, design buildings, and other structures using civil softwares like Prota Structure and the rest. On today's tutorial, we are going to be teaching you how to design this raft foundation, how to design raft foundations on Prota Structures. If you have not subscribed to our channel, please do well to subscribe to our YouTube channel, like the video, and also drop comments if this video helps you. Okay, but before we go straight into designing it, we're going to be talking about different types of raft foundations. Okay, so the first type of raft foundation we have is the solid slab raft foundation. And from the diagram you can see is the simplest form of raft foundation. It consists of a solid slab of uniform thickness, and it covers the entire building footprint and supports all the columns and if there are walls also directly. Okay, so the best time to use this is it's entirely used for very light structures, just like for residential buildings where the load is relatively very small and the soil bearing capacity is low but uniform. Okay, where the soil bearing capacity of the land you're building is low but uniform, that means throughout it's uniform. All right, another type of raft foundation we have is the slab beam raft foundations, and it consists of a solid slab and also additional beams running underneath it, both in the longitudinal and the transverse direction, forming like a grid structure. The beams will help to carry the concentrated loads from the columns. Right, so this is most suitable for high-rise buildings with substantially more loads as compared to the loads that have been applied to the solid raft foundation, and it's ideal for sites where the soil has uneven bearing capacity, where maybe some areas have high bearing capacity and the other areas have very low bearing capacity. So this will help it. The beams you're provided will provide extra strength and stiffness to handle these concentrated loads. So another type of raft foundation is also the cellular raft foundations. Okay, so this foundation consists of a hollow raft slab. Okay, as you can see, there are hollow raft slabs with internal compartments, and these compartments are called cells. That's why it's cellular. This cell can be filled with lightweight materials to reduce the weight, or it can be left hollow, and it can also be used as, as a bunker or an underground building. Okay, so it's used for high-rise buildings or structures with complex load requirements. The cellular design helps in reducing the amount of concrete used and also helps in reducing settlement. And the last but not the least is the piled raft foundations. In this type of foundation, piles are driven into the ground to support the raft. The raft spreads the load, and the piles transfer some of the loads to deeper, stronger soil layers. Okay, so this type of raft foundation is ideal for buildings on very weak and compressive soils, where the raft alone might not be able to support the building. Piles add extra stability, preventing excessive settlements. Okay, and also this can also be used in a case where you have a building and you have your piles, and your piles are closely packed, making your pile caps to overlap. So you can use this type where you can just use a raft to act like a uniform tile cap for all your rafts. But on these tutorials, we are going to be talking about, we are going to be designing the solid raft type. All right. So the first we are going to be doing is we are going to come to our plan view, story 0, because that's where we're going to be drawing our raft foundations. And remember, we are going to be designing, on this tutorial, we're going to be designing a solid raft foundation. All right. Okay. So the first thing we are going to be doing is that we are going to be offsetting. We're going to be having 800 millimeters spread of our raft foundation. Okay, spread from the wall. Okay, from the column. So you're going to offset your axis. Right click on it, offset axis. I'm going to offset it by 800. press enter. Okay, right click, offset axis 800. Okay, so you can delete that. So we're going to be offsetting from the column here, so right click, set axis 800. Okay, right click, offset axis is going to be minus 800 because we're coming down. Okay, so right click on it, offset axis to minus, okay, sorry, F2 minus 800. All right, so the next we are going to be doing now is that we are going to come to our modeling, come to polyline, because we want to create a slab edge. All right, so we are going to be fixing raft, or subsequently other people might decide to come to slab. All right, then I just start inserting. Maybe you come here, come to axis region, decide to insert the slabs. Okay, some people might do this, which is not wrong, but this is not the method they are going to be using for this tutorial. So if you come to your 3D view, you can see what they are doing. It's not wrong to impute your slabs like this for your raft. It's not wrong, but this is not the method we are going to be using for these tutorials. I don't like putting it this way. I prefer putting a solid slab round it as a whole, understand? Although it's not more economical, but I prefer adding like that so I can actually see my stresses on the uniform slab I've added. Then come to my plan and just delete this first of all. Alright, okay, so I'm going to come to modeling, come to polyline, just click the corners of my axis, the ones I offset for my raft spread. Just click on it. Okay, and just click on this. Okay, so now I have that. I can go ahead, if I can still go ahead and delete those axes I already created, so I can have a visual, I can see my raft spread well. Okay, so you can just delete that. Okay, so this is a raft spread. Okay, the blue line is a raft spread. Next what I'm going to do is to come to slab, click on slab. I'm going to be using having a 200 thick slab. Okay, you come to load, you're going to be using a lowered slab, right? I'm going to be using value for a lowered slab. And impulse load is going to be a general domestic use, so we can have an impulse load of 1.5. Okay, so going to come to insertion. I'm going to be inserting by pick a closed slab edge. Okay, so you can just pick the slab edge we did, and there you have it. That's your slab. You can escape that, come to your 3D view, and you look at it. So that is it. This is your pad, your raft, sorry, that's your raft slab. You can come back to our plan view. The next thing we're going to be doing is that we're going to be adding a slab strip. Before we analyze this, we add a slab strip. So we click on slab strip. We're going to be using, okay, so for the first direction X, we're going to be using finite element strips. Click on finite element strips. So analysis result source is not the bin analysis. We're going to be using finite element flow analysis in order to design this particular foundation. This is a raft foundation. So we're going to be using the fixed band strip. Okay, fixed band strip. So for our band strip, first band strip, we're going to be from here, all right, to here. For our first band strip, we're going to have a second band strip. Okay, and a third band strip for this direction. For the other direction, we're going to be having a first band strip, second band strip, and third band strip. Okay, so we're going to be editing that, because we use a spread. So what we're going to do is, for this first boundary we added, okay, the left side here, we want to extend it to the edge of this slab. Okay, so we are going to have a measurement for that. So we're going to right click and escape, then you right click and you see measure, Control R, just measure. We want to measure from the edge of this slab to the center of this area where we added a slab strip. Okay, so that's 4,550. You can write that down. Control R again. We're going to measure from here to grid 3. So from here to grid 3 is 4,350. Alright, so we can escape that, come to this slab, right click on the properties. So for the scope width, the first one we had was 4,550. Can update that to see. Okay, so sorry, for the left is going to be 4,350. Can update that. Okay, so you see where it started from here down to the axis 3. Okay, this is where we want it to stop. And for the right we have 4,550. Okay, can update that. Okay, seeing how it goes, so we can escape that. Okay, for the second strip, I'm going to do the same thing. Control R, measure from grid 3 to the midpoint. You have 1,350. You can measure here from here to here again, 1,350. Okay, so you can click on the grid, right click on its properties, 1,350, 1,350. Okay, so you can update that. See the spread from here to where we want it to be. Same thing with this. Right click on it, properties. So we have 4,550. And update that. Okay, and here we have 4,350. Update that. All right, so we are done with the first 3. I'm going to do the same for the second 3. All right, so this dimension we already know it to be 800, so we're going to check for this other dimension. So Control R, from here to here, 3,900. all right, so we can just click on it, right click on it, properties. So for the right we have 800 here, update. All right, 800. Then for the left we have 3,900. Update that. All right, so you see the scope, the bandwidth. Okay, Control R again to measure from here to here. So we have 1,500. Can measure from here to here too, 1,500. So you can just properties, 1,500, 1,500. So you can update that, close it. Okay, properties. Okay, so we didn't measure that this other area. We know from here to here is 800, so we need to measure this from here to here is 3,150. So click on the strip, right click on it, properties, 3,150. So we can put 3,150, update. Okay, sorry, here is going to be 800. Left side is 800, while the right side is 3,150. Can update that. Okay, so we have a band width. So if you look at it, it's being covered. A bandwidth covers everything. All right, so we can save that. Control S, save your work so as not to lose it. So the next thing we're going to do is to come to our analysis, come to your fixed end foundation analysis, click on foundation analysis, and this is what you're going to have. All right, so you can come to your post analysis first. Allowable stress of soil we're going to be using is going to be 150. going to be using a allowable stress of soil of 150. Okay, or you can probably close this, come to settings, come to your settings, come to your foundations. Unit weight of soil is 18, so you can come to allowable stress of soil and change this to 150. Alright, so we can press OK, come to fixed end foundation analysis, click on it. Okay, so we are going to be include column section in finite element model. So because once we include this, it's also going to check for punching shear, right, from the column to the raft slab, because we have a solid raft slab, right? So to know if the raft is going to fail by punching shear, if we will need to provide shear reinforcement to cater for the shear of the column into the raft. Okay, so we are going to be including column sections, finite element model. Second one is consider beam torsional stiffness. There are no beams in this slab since it's a solid raft slab, so we don't need this. You can untick that. Okay, so like I say, you can use the subgrade reaction value, so we can use this to check for the source stress checks. All right, so okay, so the next thing we are going to come here for the slab raft shell element size, minimum 500, maximum 1000. You can reduce this to maybe 25 to 50, but if you reduce it, make it smaller, it takes time for it to analyze your finite element, because this thing breaks your shells into smaller bits to analyze it. The smaller it is, the more it takes time, and if your processor speed is not strong enough, it might crash your system. So it's best to leave it at 500 to 1000. So once that is set, okay, once that is set, you can just come to floor mesh and analysis and give your system a bit of time while it creates the final element mesh and also creates an analytical model for this your raft. Okay, so mine is done. If you zoom into it, okay, zoom out a bit, you notice below here the green looks like a spring. This is the reaction of your raft on your soil. That's how the reaction is. So you notice it's almost like a spring. So if you rotate that, okay, you realize that the load from this particular column to this raft, FZ, is 128.3 kilonewtons. So that's the axial load from that particular column to that raft, and this is the moment X is 1.4 and moment Y is 1.5 kilonewton meters respectively. Okay, you can just look at that and okay, and press OK if you're done. All right, just give it time to work on that. So message says foundation beam design effect updated from finite element model analysis model result. So you can just click OK once that is that. All right, so analysis is being complete. You can save. Usually I just save column wall transfer to file, save this, right? And I can also display analytical model. Just click on the display of analytical model. All right, so we can see the behavior of our raft with the loading and okay. So this is a raft. Okay, so this is the displacement of a raft with the loading. You can just do the animation so you can see the movement of it. So this is the movement of the displacement. Okay, so you can just stop that. You can just stop that. Okay, that is it. Okay, you can look at the diagrams, click on the diagrams to know. Right, so okay, this is not lead, so you can come to contours. It is where you can just click at top so you can look at, so you can understand properly how the contours are. So click on contours. Okay, just to look at, to know the forces. So this is how it looks like, the forces: F1, F2, okay, so this is the bending moment, local bending moment, M1, This is it. Maximum blue here shows minus 13. Okay, this is like a legend to see and know the maximum and minimum displacement for moment M1, M2 also, and M12 for torsional moment. Okay, so this is the legend to know the contours and how the raft slab behaves on certain loading conditions. Okay, so I'm going to do a tutorial to explain how this contours and what it really means, but for now you can just leave this and can end this. We can come back to your story plan. Okay, once that is that, you can just you can right click and you update your steel bars. Okay, so it's going to use the finite element analysis model now to provide reinforcements for your raft slab. So if you zoom into it, you realize that it provided Y12 at 250. It's doubly reinforced, so it provided Y12 at 250 and Y16 at 150. So for the top bar, it provided this, and bottom bar provided Y16 at 150 for this direction. And let's check for the other direction. Provided same thing, Y12 at 250 and Y16 at 150 for the raft for this building. Okay, raft for this building, so that's what it provided. And come to your 3D to look at it. So this is how it looks like. Next thing you should do is to make sure you check the reports to make sure that it's analyzed and it passed, that the total load that is being applied to these rafts, okay, it's that the bearing capacity is able to carry that building. Okay, most people don't check this, but you need to check this. It's very, very important. So you come to your drawings and reports, come to your finite elements foundation report, click on it. Okay, so please select the load cases and combination to be reported. I want it to report the envelope, the max. So it's going to check which of these combinations produces the highest loading condition and the highest moments. Okay, so to help us better understand. So okay, add notification summary to report, add column. Okay, final element. So we don't want it to add required rebar, wood, armor, so you can just untick this and tell it to generate a report. Give it a few seconds while it generates a report for you. Okay, so it's loading for the reports. Okay, so you see you have the soil parameters. The allowable soil pressure we had was 150. The soil vertical subgrade coefficient was 50,000. So this is the grade of material we used was C2530, and the foundation rebar was, the grade was 410. Okay, so you see the base pressure. This is something to look out for. The base pressure and moment. So the maximum base pressure is 105.5, which is less than the soil bearing capacity. That means the soil bearing capacity, that means this raft foundation, the soil is able to carry this building. All right, so you see it ticked, it's correct. Most people don't check it, but it's very, very important to check this. All right, it's very, very important to check this. So we can just go through it, and you can, if you check this, okay, most of these are not even needed, so you can just realize the contour that I told you to check. All right, so foundation design moment contours. So in the next video we are going to be explaining this. So this is the moment diagram, what it looks like. It depends on the strip. Okay, cutting it strip by strip. So our first strip, okay, first strip, load case envelope. So this is what the moment looks like, and the shear force diagram, this is what the moment looks like. Okay, it's important to add your strips and do it the way we did it, so you can understand this better. I'll be making a tutorial video how to explain this, so you can understand what those contours stand for. Right, so if you want to convert this report to PDF, you can just click it, compare it to PDF, and that. All right, so you can close. So this is it. You can also check this again by coming to our design, come to slab analysis and design. So we can just check that again. So you can just slab strip and delete and reselect all bars, just to be sure. Okay, not okay, slab not found, so that's not even a problem. Okay, so I think I deleted some slabs. From the model. Okay, so that's not a problem. So you can just check to make sure that what you provided is okay. So that's it. So thank you for watching. That is how you design a solid raft foundation with Prota Structure. Please do well to encourage us by subscribing to our YouTube channel, liking this video, and also dropping comments. Thank you very much.